Hello, Physics 2 students. In this video, I want to discuss how to find the magnetic field for an infinite solenoid from Ampere's law. We've already seen a solenoid, and we even talked about what would happen in the limit when it became long, but we only evaluated the result at the very, very, very center. So a solenoid looks like a long string of loops, and we will assume that it has a length L, which tends to infinity, and it has a number of turns, which also tends to infinity. And we're going to assume that the turn density, which is N divided by L, is constant. And that has the, well, that will lead to a simple result. Now, before, way back, we found that at the center, that the magnetic field was like mu naught times the number of turns divided by the length times I. That was our previous result. And we're going to reobtain this using Ampere's law. So the first idea is, well, first we have to draw a picture of this. So let's imagine you have a really, 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 really long solenoid. Tending off to infinity in either direction. And we've already seen that the magnetic field lines for this pattern will form horizontal lines in the middle, but if you can never reach the end, then they're never going to start bending because they can never get around the edge. It's like they can never leak out. They're trapped, confined to live in the solenoid and run off to infinity. All right, so these lines, so the magnetic field lines must, they must be parallel. And they can't bend, and they're trapped inside. Because they would have to get around the edge, but if the edge lives all the way off at infinity, they'll never make it. So that tells you immediately that the magnetic field here must be 0 on the outside. There are no field lines on the outside. All of the magnetic field is concentrated in the middle. All right, great. What we want to do is to use Ampere's law to do this, to find the magnetic field. Okay. So I have magnetic field lines, try to keep them straight as best I can, which run like this. And what I'm going to do is draw an Amperian loop, but rather than making it circular, because this has a nice rectangular sort of shape to it, I actually will make my Amperian loop be a rectangle. And I'm going to let this rectangle have a length lowercase l, which is just a finite number. This is just a quantity which is going to cancel out at the end of the day. So let's evaluate. So Ampere's law says integral of b dot ds around this loop equals mu naught times the current enclosed. Now, when we do this integral, we see that there's going to be some contribution here because B and ds point in the same direction. Here on the two sides, the magnetic field and the arc length vector are perpendicular, so their dot product will give 0. So you're going to get no contribution from the sides, and then of course there's no contribution to from the outside because there's no magnetic field on the outside. So the only place where this integral receives a contribution is right here. So this is simply going to be V times L, because this magnetic field can't vary. It has to be parallel to that line. And because they can't bunch up or squeeze, because they can't bend, we expect the field strength to be constant along that curve. And that must equal mu naught times the current enclosed. Well, because I know the turn density, I can say the current enclosed is the total current, I, times the turns density times L. This would be the turns per unit length times the length associated with this Amperian loop. And as advertised, those cancel, and I'm left with the magnetic field of the solenoid, it's an infinite solenoid, equals mu naught I times N, or remembering the definition of N over here, it's the total number of turns divided by the total length. I get mu naught I big N over L. And I promise you, if you go back and look at what we had to do to get the same result, but just for a fixed point, you'll agree that this is much easier. In fact, for an infinite solenoid, the magnetic field becomes constant. Everywhere throughout. This is quite analogous to the role a capacitor played for electric fields, where the electric field was constant. In a solenoid, in an infinite solenoid, the magnetic field becomes constant throughout. Okay, very good. We are going to do one last example, which is of a toroidal solenoid. And then that'll be our last kind of basic configuration that we can calculate things. And then after that, we're going to turn towards induction and time dependence. See you next time.